Okay. Welcome. Welcome to the secret lecture. Uh, Basically, I'm getting enough questions about the assignment 2 enough that I just want to go through the code that I gave. Um, so one thing to know is that this is code uh, that I wrote myself, right? So I recognize that there is always a blind spot in code that you write yourself, in that it's logic that you understand. Um, and it doesn't mean that it's logic that everyone understands. So I just wanted to get that up front. So what I'm going to do here is I'm going to go through basically bit by bit of the assignment, and as it becomes relevant, we will go through the code itself. And I'm going to explain the code to the best of my ability. Um, and part of the purpose of this assignment is to kind of see what it looks like when you actually simulate a robot, because it's very much the case that it's not always going to be as straightforward as you think it's going to be. Um, let's see. Okay, I can't. So continuing on, so I'm going to explain kind of the logic and why things are the way they are, because at first glance it can seem a bit convoluted, but there is a reason that everything is the way that it is, and I'll try to elucidate that as we go through. Um, so starting out, just going through this, there's a few things files you will be modifying run. So as before, run is kind of the top level thing that is going to run. And when you run this, it's going to spit out a bunch of stuff. And so just looking through this, uh, first we just reset everything to zero right here. This is where we add all of these folders. So you can see they're kind of grayed out. When that's run, they're added to kind of the list of references the that MATLAB is going to be looking at. This isn't too important. We have an object called symparam. So this is going to be under configuration. And essentially what this is it's a collection of all of the robot parameters. Um, and what this means is that it's all in one place. Now, a lot of times what I'll do is in here I will have it so that it it'll actually load stuff from an Excel sheet, but I don't do that here. But you can see here that it is setting where everything is. Um, and I should have added a explanation there, but whatever. Going down, we now get to the initialization. Um, and so what these are, this is what you're going to be using to switch. And this is actually where I have a misstatement here. Initialize environment. Um, this doesn't exist at this point. It's all rolled into place robots. Um, so you can ignore that. And really anything that is listed here you can ignore. But going through, we have a script draw world. This is a very simple thing where it goes through and it's just going to draw every single robot. Every robot has a method called draw self, and that sets the window bounds. Um, Going down, X condition sim step. This is how you will take videos. You'll uncomment these. And then going down here, this is most of this you don't have to worry about, right? All of this is for extra credit. And then this is where the robot actually runs. And so you see here that it's going to go through the robot array. It's going to run the robot logic. The robot logic is going to output like this is the direction I want to go, right? And this is the communication I want to do. Now, very commonly, what you have, you have this hierarchy where you have kind of objects under the simulation itself, right? So you have the simulation, then you have the objects in there, and generally the way you do it is that you don't want anything to be talking to each other across the level. And so the easiest way to handle communications is to essentially just swap everything. And you can see that's what's happening here, where you have the vector that the communication is coming in from. All of this is essentially like swapping the messages, loading in how far away it is, what direction is it coming from, etc. And the movement handler is another piece of code. You might think, oh, okay, the robots can just update their positions, but what happens if a robot were to move into another robot? And what you do here is you go through and you're just going to check whether a given position is full. And there are some. Oh, sorry. And then what you do here is you go through and you just update your positions based on where you are. Kind of if a given position is empty, you do that. If you get an error, there's an issue there. It'll tell you something. Again, when you're running stuff, it's good to do pause on errors, and it's going to pause, and you're going to see everything that's wrong over here. Yeah, and so you see here that if it's far away, it does that. Now the thing here is that we're going in an ordered way, so you go from robot 1 to robot n. Typically you want to shuffle that just so that you don't end up with kind of a bias towards lower IDs. And then you draw. And that's essentially it. So, run.m is pretty simple. It just starts out, it will have the robots kind of process what's going on, handle the communications, handle the movement, and that's all that's happening there. Object robot logic, this should just be robot logic. Now if you look in here, we have kind of message flag, robot logic. Now robot.m represents the physical robot, right? It represents the physical embodiment of the robot, and we separate that out from the logic portion. And the reason we do this is just so that it's easy to add new or different logic to the physical robot itself. You also see that I have two different types of messages. I don't believe you have to change these here, but essentially what it is that instead of kind of forcing everything to be specific numbers, we create a message object so that the code is more modifiable easily, right? So if we need to add a new variable between robots, instead of worrying about is every robot setting that, we don't have to worry about that. We just update this object, and if things are set, they're set. Otherwise, you can set them to 0. So it's just good practice in simulations to have any communication messages be represented as objects. Okay. Robot parameters, sim parameters. Yeah, so this is everything from this is a dictionary, right? What distance do you want to orbit? What is our communication range? These are things you're going to be updating later on. We went over these. And then draw robot paths, also don't worry about. I don't remember if that's in this version. Okay, so number 1, you're going to go into robot logic .m. And basically from here on out, we're only going to live in here. Now, going down, what you see is that you have a number of properties. And what these properties are is basically everything that is used to control the robot behavior is here. You can think of this as the robot's like computer memory. And so we're defining all the variables, that all the measurements, all the outputs that are used. And so going down here, during the initialization, you're going to configure your role, you're going to load the parameters. This logic is for seeds to change their color. have that. Initialize the communication out, so you're tracking what your previous communication out was as well. None of this you need to change. Going down here, we get into most of the logic, right? And so run logic, remember that's called every step in run.m. This is essentially where the logic is going to be routed, right? So there are a bunch of different behaviors that we're going to be doing. And what you can see is that we're going to be changing where what behaviors we do is going to set what logic we're going to run. And you can see in here when we're doing place robots, it is setting what those roles are there. So you can see we initialize everything to basically 0. And then for part 1a, you do all this, and then you just see that it's essentially a switching statement. Like, if this is your role, then you do this. Otherwise, you do this other thing. Yeah, and then you're returning the desired motion that you want to do. And you clear the communication. But in here, the main functions, the methods, you start out with part 1a, right? And here, you're setting some value, and let's see what part 1a is. Oh yeah. So essentially what it is that you're going to just be tracking, and you're going to say like, okay, I want you to go forward for 90 steps, right? And so you'll set some value to 90, and you'll set the out forward, whatever, out spin, and then after some point, you're just going to continue, and you're gonna continue on to whatever other logic. So what that's going to look like is that you're just going to kind of go around, spin around, whatever. To show what this looks like, right, so it went forward, and then it kind of made a loop-to-loop. So that's an example of what part 1a looks like. So hopefully you have a good idea of what's expected there. Part 1b, what that looks like is we're going to have a planet that's kind of going around the sun, and it's orbiting, right? It's kind of sort of orbiting. It's good enough. You see here where you have the direction, you have the distance. You should always be moving forward, just because that's how orbiting works. But then you need some sort of ability to spin at some rate, right? So you have out move, spin, out move, forward, right? These are the things that you're going to be using in order to determine what speed to move forward, what speed to turn. And I'm okay with showing what that part 1a looks like, right? So you see here, this is right here. So you see that I essentially just have out move forward and then out move spin. That's just how I set things as it goes. In this actual example, there's going to be some stuff that is slightly different, because I changed the names to be a bit more friendly in this. But we see how that works in Logic Planet. Logic Seed, I don't know why there's an R there. That needs to be deleted. Yeah, so going down, we've done 1A, 1B. This note here, I've had someone explicitly set the XY position of the robot, and it's just like, no, that's not the point. The point is to react to the distance, right? As long as it kind of goes around, right, and it's obviously reacting to the distance, that's what I care about. And that's true for basically the rest of this assignment. Like, I'm looking for evidence that you understand how to implement these behaviors. And I mean, the thing is that these behaviors are not themselves that complex. But what you're going to see is that even though these behaviors might seem simple, their implementation can be not simple. So continuing on, what I've recommended to people is actually to skip from part 1 to part 3. The reason I go from 1 to 2 is that with hop count we're only considering really the messages, whereas with flocking you're considering everything. But I think people find flocking a lot easier to kind of get in their head. So I recommend, if you're having trouble with part 2, just go into part 3. Unlike assignment 1, the parts are not scaffolded, right? The only scaffolding here really is that part 1, right, to introduce you to all the basics. But hop count and flocking, they're independent. All right. So going down here, we're going to have run logic, general hop, and hop count propagation. What you find is that with the seed, it's super simple. You're just outputting what your ID is. Now, most of the actual logic is in this hop count propagation. The run logic general hop is where you're going to be doing the localization for part D, I believe. Yeah, and this is actually, so this is something where it works with 3, but with 1 it might not. So what you can do here is to do and that's going to align things kind of regardless of how many nodes and sorry, how many hops and how many seeds there are. So that's an easy thing to change. That fixes that. Okay, continuing on. In here you can set the color, right? So this is a RGB triplet. So red, green, blue. If you need help choosing a pretty color, you can open up Paint, and this is actually one of the annoying things. I can do this, and I really like, this is a beautiful blue, though I guess I should show School Pride, and we're going to choose this as the NGIT red. Right, so this is the RGB that I do. Now the thing is that it's normalized 0 to 1, so you can see that it's 0 to 255. Right, so you just divide the number by 255 and you get it. Anyway, continuing on here, the way to read this is that you have the seed locations, right? So this is going to be XY. So we're kind of going on to 2D, right? So when you're ready here, this is the gradient descent. And so we start out with the position estimate of 0, 0, and you can make that be whatever you want. And so seed location 1, this is just to make it more readable. It doesn't really matter. But this is going to be, an XY double. Sorry, not double, a pair. Now what you're going to do is you're going to take essentially all the hop counts and all the hop nodes, and that's going to be that's going to be kind of a list of all the hops. Now, one of the things that I've done here, and this is something that might seem overly complex, but it's I make it so that the seeds can have any ID number that they want, and if the and there can be as many seeds as you want in this. That's why I do it the way that I do it. Um, but yeah, so here you're calculating the distances. So remember from the lecture, the hop count is a good heuristic for the distance. And then here, this is think of this as position error, right? So PE, position error. And then this would be position error x, so right, so if we step a tiny bit in the x, if we step 1 in the x, what happens to the number? If we step in the y, what happens there? Right, so you have to calculate what are those positions, what are the errors associated with that, and then based on the errors for x and y, right, you update the estimate. And you can print it here, and this is yeah. So sorry, this is not position error. This is just the position estimate, right? Position estimate with a step in the x, position estimate with a step in the y. You calculate the errors down here. You'll name those variables whatever you want. Continuing on. Going down to hop count propagation. This is where it happens, right? So remember that we're not assuming a certain number of seeds, right? We're not assuming a certain number of hop counts. And so what we need to do is we need to keep track of which seed sees which hop count. And so you're going to go through length comm, right? So comm is going to be an array of messages, right? So for every message that you see, you're going to go through. So it's going to go through and it's going to see, okay, what seed IDs is being sent from the message, right? So if the message sees seed 2 and 3, that's what's going to be entered here. And it's also going to enter what is the hop to those seeds, right? And that's going to be in the same order, right? So regardless if the message says, seed 97 hop 2, seed 5 hop 3, right? So it's going to be 97 5 and then 2 3, right? So they're going to be in that order regardless of what the number is. Okay. So it's a general case. Hopefully you understand why I did it like this. Loop through all hop origins specified in this message, right? So we're pulling from this observed seed IDs, right? So this is for every seed, and this is for every hop. So we're going through how many seeds do we see? We're gonna loop through that, and we're gonna ask which hop count are we paying attention to. So you're gonna, for the specified hop count, JJ, and this is, let me rewrite this for the specified seed. That's going to be yeah. So we're looping through all that. That's where that is. So the first thing that we do is we're going to search through this. So all this is going to do. Yeah. No, so it's finding out which seed we're looking at. Right. So we have this personal list of all the seeds that we've seen. And we have the list of seeds that is being sent from the message. And so we're we're essentially just saying, okay, we're focusing on getting everything into this local seed list. So now for hop index, right? So we're looking at a specific seed at this point. So for observed hop counts, right? This is the current hop count that we think we have. And what we do here is we are going to go down and we're going to it's late, I just taught. The observed hop counts is the current hop count that the robot thinks it has, and hop seed to message is the new message that has been observed, right? So observed hop counts, hop index. So let's say that we have a situation here where we have a message that is essentially, seed number, hop count. So we have this. So when we're saying observed hop counts, right? So let's say that we currently have a list that is, seed 9, seed 3, right? And hop count 1, hop count 4. Now we have this new message coming in, right? And right now we're looking at this one here, right? We're interested in this. And so this new message, and this is not how it's arranged here, it's just easiest to represent it like this. 3, 2, right? So this message sees this, right? So we're looking here, and so the observed hop counts for hop index is referring to this 4 here, right? So the robot has this. This is the new message that's coming in. So it's saying, okay, I'm looking at this hop, right? So we're looking at the hop that matches here. That's where hop index comes from, right? It comes from that. So it's doing this find, right? And it finds where is 3 within this list. Okay, it's in the second thing, so therefore we're looking at this hop. And so we essentially have a 4 and a 2, and we need to run the hop count algorithm on this, right? So if you remember, it's the minimum observed minus 1. So plus 1. And that's all you need here, right? So if you're doing a huge amount of work in programming, you're doing it wrong. So that's hopefully that makes sense what the logic is here. Now consider a situation where you have this, where you have 9, 1, 3, 4, and you get a new message here that is 17, 6. Or because it's what the kids like these days, you got 6, 7. I don't understand it, but this is how I relate to the youth. First person to explain it to me, I'll give you like 1 point extra credit on this assignment. Anyway, so here, right, what we're finding is that if there is a hop index, right, we're going to do that. If that fails, though, what we see here is observed seed IDs is already this, right? So we already have 9, 3, and at the bottom, we're loading in this, right? And so we're saying, okay, that's 6. So there's nothing you have to do here, but that's all this is doing is it's adding this. Now, I guess it's supposed to be wide instead of tall, but whatever. Now for observed hop counts, right? This 0 is wrong, right? But we already have this hop count to this seed, and so we know what to put in here, right? This is going to be 1, 4, and then 7 plus 1, right? That's what that's going to be. And so that's really all there is to it. That's all there is to that. And unfortunately, this is a very common sort of thing with any sort of simulations, any sort of programming, where the actual logic is very easy to explain, but you have to add in all this safety code. I think I've still told this story in class, but one of my professors in graduate school, he explained how he made a super fast controller, and the actual control code was about 20 lines, but to make sure that everything was safe, he had to write like 2,000 lines of code. So there's often a mismatch between the stuff that's useful and the stuff that is necessary. Okay, so we did this. You can see here we're going like this, and if I go here, I'm going to so that's what you should see. That. To see, we're adding these seeds, and you can see how it's kind of going like that. After a certain number of time steps, you can see they're all localizing relative to each other, and you can see it's jumping around, but that's fine, right? It shows that it's doing what we think it is. All right, flocking. Flocking, this is what it looks like. I've not tuned the parameters here, right? That's one of the things to understand, is that I've not tuned the parameters. So you'll need something that is better than this. But you can see here how stuff is generally grouping together. And you're going to be playing around with a lot of the parameters, trying to get something good. It doesn't have to be great, just as long as it's doing stuff. Robot logic, I've given you these place robots. Cohesion, communication distance, R is 10. Remember, that's in configuration up here. So here, what it is that you have some vector for cohesion, and you have to go through and essentially set what cohesion should be. Right? What rule do you have for directions and distances? And directions is always relative to forward, right? So if I'm facing this way, direction is going to be essentially I'd have to double check, but I believe it's 0, 1 would be the direction. If I'm pointed this way, it would be 0, negative. 0, negative 1, right? So this would be 1, 0, 0, negative 1 for direction, and then distances is the distance there. So you'll have to set that, and you see here that I'm setting everything to a value of 1, and this is going to be useful in a bit. And actually, this is something that, if you're getting stuff failing at this point, just add that. One big problem I've seen is that people actually make the alignment be opposite what it should be. So just make sure that it's correct. And this is where we essentially say, oh, for alignment, we only care about the spin. And so these lines here are really where you're going to be doing the code. And then this is where you're going to be doing some investigation. You're going to be figuring out what the weights are, how you're going to combine these virtual forces to the movement vector, and the rest is nothing. Right, so we have something to catch errors here. This is making it so it can't reverse. Right, we have a certain minimum speed. You can set that to whatever, and that's essentially what it is. So you'll go through and do all that, and then I'll let you do extra credit yourself. Okay, I've spoken enough, so let me know if there's anything.